Hi guys, today I'll be showing you a project that I've been working on for the past several months. It's essentially an emotion classifier, which is a convolutional neural network that takes an image and classifies the individual based on their emotion. Right now I have 8 emotions: anger, surprise, disgust, fear, neutral, happiness, sadness, and contempt. But I'm working on expanding that to other emotions. Um, Here's the main document, I guess, that I'll use to go over our entire project and what it's going to entail. So we mainly extracted images from 8 different categories, like I discussed before, from a dataset that we found online. And let me just quickly open it up to show you how it is. So over here, just a set of images for classifying facial expressions. And I found this to be really helpful, especially since it provides a data set. Look at how much images this has, and essentially they provide a classification for each of these images so you can actually classify them later. So if you guys are getting interested in starting and actually building your own emotion classifier, I definitely suggest that you get that GitHub link a check. So one problem that we mainly faced through this project was that some categories like neutral and happiness had more images than others. So essentially I synthesized new images by changing the factors like contrast, color, and sharpness and added it to these categories with the fewer images. So over here, if you go to our data augmentation, processing images over here, and of course I split up between train and validation. So essentially we have the sharpen, contrast, color, and then rotate. And then over here, I essentially just, this is basically just the rotation. So it can either be 0, 90 degrees, 180 degrees, or 270 degrees. Our contrast was bounded between 0.8 and 1.2. Same thing with our sharpen and color. And essentially this is just running through the code. And yeah, this essentially just creates different contrasting images, because if you remember, we don't have enough images to actually run off. CNNs need a lot of images and a lot of data to actually build their classifier. So essentially what we did here was create more images for the CNN to run on. And also we discussed that neutral had much more images than anger and surprise, fear, and disgust. As you can see over here, this is 2,784 images, while anger simply has 92 or 142. So we basically synthesized new images mainly on anger and surprise, disgust, fear. And we kind of just left neutral and happiness by themselves because there were already so many images from them. And we subsequently split the data into training and validation sets, like I said before, using a 60-40 split. Um, there's approximately 4,000 images in each category in the training set, and approximately 2,730 images in each category for the validation set using our 60-40 split. So training and validation was essentially just used because it's pretty commonplace to have that inside of a CNN. Afterwards, we also, after processing the images, we resized them to a 350 by 350 to a 50 by 50 to allow for faster model training time. And this is essentially just for preference, but we had extremely low time and budget constraints. So these images were just resized to have faster operability. Some of our models took over 6 hours to train, and if we left the resized images like they were, it would have taken over 40 days to train. So we essentially just did it for time and for the time of those constraints. And in order to find the most predictive model, we actually implemented 3 approaches. Using pre-existing Sagemaker image classification algorithms, utilizing AWS Recognition to predict the personality of the testing images, and then building a convolutional neural network from scratch using Tensorflow and Keras. I'll go into more of these in detail later. I just want to quickly go over the resizing images. Sorry, that was the wrong link. Let me go here. So essentially, we just resize the images essentially by just splitting them up in the train and validation. There's nothing really special about this. Remember that I will link the GitHub link repository in the description below, so you guys have a better understanding of where everything is, and you guys can actually like try out and test the code for yourself. So let me just get right into it. So first we use SageMaker training jobs. So to give SageMaker the access to the content of these files, we shifted the training and validation sets to S3 for better operability. So if you guys don't understand what I'm saying right now, I'll just give you a brief overview of what I was using. So I basically used AWS, which is essentially a cloud computing service, which basically speeds up the running time and operability. So my local computer unfortunately couldn't handle these image classification data sets. So I found that running it on SageMaker, which is basically AWS's way of running Jupyter notebooks in a secure environment, because the cloud has so much storage and so much compute power that we can essentially just run it on the cloud, and none of our local computing power will ever get used. So I basically switched to AWS SageMaker in order to actually get the fastest operability. S3 is essentially just the storage service that is used in order to store these files. So to give SageMaker access to the content of these files, we shifted the training and validation sets to S3 for better operability. Then we used training jobs, which used pre-built image classification algorithms to create a model based on the images sent to them, 350 by 350, using an MLP2X large instance. So an MLP2X large instance is essentially the instance that's basically running our SageMaker training job. Instances are basically the things that provide the computing power to actually run these models. And MLP2X large instances are essentially geared towards actually providing more operability to S3 because they're essentially just for compute power and for machine learning. So the hyperparameters and inputs that are changed accordingly in order to provide the most optimal model. We use 15 epochs, stochastic gradient descent, and 53,336 training samples. Note that training jobs are a built-in function inside of AWS SageMaker, which is really cool. So essentially, we didn't do any coding for our CNN. These SageMaker training jobs actually already had a built-in image classification algorithm. And essentially, we just fed in the data, or fed in data with the labels and the images, and essentially they just trained it. And with the new images that they got, they basically just make their best prediction. So the train time for this model took approximately 5 hours, with even the and we tried this actually with the 350 by 350 just because of how efficient the SageMaker algorithm actually was. And then we finally uploaded it to S3 to validate its accuracy. What we found was that the SageMaker training job had an overall training accuracy of 88% and a validation training accuracy of 81%, which is surprisingly good, to be honest. Because we actually, a lot of our images were based off of contrast, brightness, sharpening, and just changing the resolution. In order to test the training job on the testing images by the dataset, the model is recompiled into a Jupyter notebook for further testing. So you guys don't really need to understand what's going on over here, but this essentially just shows that our thing was 81 to 88% accuracy. I suggest you guys look at the GitHub repository for more information if you guys are more interested in learning more about SageMaker training jobs, or to search it up online. There's lots of good information out there online. But essentially, the SageMaker training jobs, just to give a brief overview of what it was using AWS Cloud Compute, which is essentially a cloud computing service where you can kind of offload all of the external work that is used to run these machine learning algorithms onto a cloud-based server. And these training jobs already come with built-in algorithms, like image classification algorithms. So essentially, all you do is put in all of your supervised learning data. It's really important that this is supervised learning data, that you have a label and an image, otherwise this won't work. You basically just pass in your supervised data. It'll train using its image classification algorithm already, and essentially it'll spit back an output according to what images that you produce. And now we'll move on to the next thing in our thing, which is AWS Recognition. So AWS Recognition is also another built-in service from Cloud Compute. So Recognition is really useful in actually identifying images, figuring out whether the unique emotions, so whether it's angry, surprised, disgusted, fear, calm, happy, sad, or confused. It's a little bit different from the emotions that were shown before, but over here, AWS Recognition, it kind of takes the training jobs one step further because there already is a pre-built algorithm that determines these emotions. So what I'm saying is basically we don't need any training input, so we didn't need any of the dataset or any of the supervised learning images because it was already trained using so many images. So essentially we just use recognition to train and test our model, and we mainly focus on the emotions section of the recognition like we're talking about. Recognition has so many aspects to it. You can identify glasses on a person's face. You can identify whether they're They have dimples, they have freckles, they have a large jaw or a small jaw. There's so much you can do for recognition and facial recognition. But in this case, we were just using it to identify emotions. So recognition often showed up multiple emotions, so we simply took the emotion that had the highest probability according to recognition. And that makes sense, right? You can be angry and surprised at the same time. So we essentially just took the one that had the highest probability of being true. So the accuracy of the AWS model using recognition was surprisingly actually 60%, which is lower than our Sagemaker training job. And we were thinking, because this was not really optimized towards our code, so the testing images that we gave Sagemaker recognition, they were really, they didn't really, they kind of just based it off of the images that they got from their supervised training jobs, but they didn't really know what to do with these testing images because they never saw these images before or images close to that before. So that's why they were unable to deal with the images as well as this training job had before. So just to sum it all up, AWS Recognition is a built-in service. It's different from SageMaker training jobs because it's the model is already trained. Like you don't need to put in supervised learning data in order to actually train the model. And even though this is by AWS, which is a pretty reputed service, this unfortunately gave only a 60% accuracy, which is pretty surprising considering that recognition is commonly used in many platforms around the world. And the main reason that we actually thought that this was the issue was because they didn't really understand the images, and if it had more experience with the images, maybe if it got trained with these images, it would have a much better accuracy in the long run. Lastly, we built our own CNN using Keras and TensorFlow. We essentially made a CNN model that would accurately predict the incoming text images fed into the model. The CNN model consisted of a combination of convolutional, max pooling, and dense layers, and our main activation function was ReLU in order to actually increase the computational runtime. Our main thing at this point was just to increase the computational runtime because it would have taken a long time if we implemented any other activation function or even input any more convolutional layers. But yes, surprisingly, we found that the accuracy was getting better and better. And essentially at the ending, I think we got an accuracy of 87%, which is pretty optimal. And just some noticeable tweaks were our batch size was 16, our number of epochs was 12, and our measurable loss was categorical cross entropy. If you guys want to look at our code, remember I link the GitHub in the description. But it's all pretty self-explanatory as well. And lastly, we actually tested the model. So this is our CNN model. So this is actually how we figured out that we got the 87% accuracy. So essentially, we have these testing images, and we just run through the entire thing. Again, I don't want to go through the sections of this because it's already being a pretty long video. But you guys can always go through my GitHub and check it out later. So I just want to quickly go through some challenges, and maybe you guys can figure out how to fix this later. So during this project, a repository of images were used for training the convolutional neural network from a pre-existing dataset. And due to the size of these images, we actually converted it from 350 to 350 to 50 to 50 so that our model will train faster. And we also had to consider cost and time constraints. So this actually reduced our accuracy by a lot. And hopefully, we're hoping in the future to create a larger instance because the MLP2X large instance did cost a lot of money. It was approximately $1 per hour, and if you had a larger instance, we definitely could have run the model faster, had a better accuracy, made our images a little bigger. And another thing was the accuracy of the dataset itself. We believe that the dataset actually had some inconsistent or low quality images, which and due to time constraints, obviously we scoured the internet like extensively, but we couldn't find any that really suited our needs as well as this one. And if there was a more accurate data set online, the accuracy could have been much higher. As you can see over here, the accuracy of our classification was 56%, while our training accuracy was 98%, and same for AWS recognition. So it's pretty obvious that there's a disparity over here, and more analysis is needed. But it's probably because our anger only had 90 images, while our neutral only basically had 2,000 images. So it makes sense that there's such a wide disparity between our accuracy of the classification and our training accuracy. So further steps for this project are definitely to expand to other emotions. So we're going to use a more optimal data set, most likely maybe making our own data set using some ground truth images or finding a better data set online. Secondly, we're gonna expand this to other cloud computing platforms. GCP and Azure also have great image classification algorithms, and it'll be great to see how they would actually vote against these AWS's Recognition and also their Sagemaker training jobs. Um, and lastly, we're definitely going to try to reduce runtime because our runtime and time constraints are extremely low. So we're trying to figure out how to maximize accuracy while lowering budget and time constraints. And those are our main three pillars that we're going to focus on during the next few months. Um, Please put in the comments below if you guys have any questions. Remember that my GitHub is linked in the description, so you can always go there if you're feeling like you need to just run through the code again. Maybe you want to try out and test a few of these things for yourself. Note that in my GitHub, I did not include the datasets that I used, but it's all on the GitHub repository. And if you just run through the code, then you should be able to actually and just follow the steps provided, then you should be able to produce the same result that I did. Unfortunately, the datasets were a bit did take up a lot of storage space, so I really could not put it on GitHub. Yeah, but if you guys have any comments, please put it below, and yeah, I'll keep you updated. Bye.